Hello, everyone. Good morning. Welcome to today's session. So hope you're doing well. So last week we spoke about we talked about custom data sets and going modular, in which we looked at how you can deal with data sets that are not of like the standard formats in like different ways data sets can come in, and how you could structure your code in which you would be able to write much more like clean code that will help you reuse them over and over again. So today we'll be going a bit differently, and we're going back to model training, in which, uh, unlike previously, we've been using models in which we build from scratch, but in today's class, we're using like an already existing models, and the hope that it will perform better for us with time. So I'll just give some bit of motivation along the way, and we discuss how we can do that with PyTorch. And also feel free to ask, if you have any questions, feel free to just ask any questions on the chat, and you can also unmute at any point in time, Nishan. Yes. So today we'll be looking at transfer learning with PyTorch, how you could leverage PyTorch for transfer learning. But it's quite important to understand the concept of like transfer learning. So transfer learning just simply means like using an already existing model and using that model for your own data that you have. So let me just give like some kind of illustration. So imagine you have a task of building, perhaps let's say it's some power plant. So let me just do some illustration here. So let's say you have like a tax of, let's say you want to build a power plant, and you have like 3 people in which can help you build the power plant. Maybe first you have maybe some layman who doesn't have some technical skills, and you have, let's see, an electrical engineer, and perhaps you have a doctor here. So among these 3 people, if I were to ask you, which one of them would you ask to help you build this power plant? And take into consideration, you can train that person with some particular skills he need. So which person do you feel like would be best for you to train the power plant? You can just quickly type out in the chat for interaction. I can see Yahya has typed out. So Yahya said electrical engineer. Any other suggestions? There's an answer from Sophia, also electrical engineer. So yeah, that's very good. Yeah, so I will just quickly go into why my assumption of why you feel is an electrical engineer. I also feel the same also, because with an electrical engineer, even though he might not have the like elaborate experience of building power plant, you have the basics, and from that you can easily build upon that. So it's much more cost effective for you to train him because he has the prerequisite knowledge about it, and also it takes you less time to train him about it. So that's like the idea also of transfer learning. Maybe you take something that's already been used in another domain, then you apply it to your data sets. So it can closely align to your data sets, or it can maybe vary a bit, but based on that training, if your base model, we call it like base model in this instance, is good or it relates, so it helps you save a lot of cost and you don't need as much as significant data as you need. So I'll just, yeah, thanks so much for the comment. So we all agree it's like an electrical engineer. So yeah, let me just clear this. Yeah, thank you so much. So in typically, what transfer learning means is you take a model that's already been trained on some like large data, and the assumption is the model has already learned some existing patterns, underlying patterns within that data, and you can easily apply that model to your new data set that you have. So it can be some different domain, and in that sense, we call it domain adaptation, but don't worry about that. Yeah, we don't need to discuss that. So it just means, let's say you have, yeah, so let's say you have this pipeline here in which you have a model, and that model has been trained to do this, to classify between, let's say, cat and dogs to identify them correctly. And you have some bit of like inputs coming in to the image, to the model rather. You have like an input image. So all this, all what your model can do here is just to learn to predict like cats and dogs. So, but for instance, let's say you have a much more bigger data set or data sets of different classes. So it could be data sets of having to have something extra like perhaps camel or other type of animals like let's say panda in this case. So before this, your model has not learned this, but your new data set that you have has this. So what we are trying to do is how can we better train this model here just so that it can adapt to, let's say, all these classes that we have here. So that's what we call transfer learning. So it doesn't need to be exactly like animals. So it can be something different. It can be identifying different objects. So because our model has learned to identify those features that are common to our the animals we had in mind, or initially that it was initially trained on, which is like the cats and dogs. So it can have learned to identify features such as like the curvature of the face, the type of hair, and different distinct or fine-grained features. So after we do some extra training with our data sets, then it will learn to perform much better in classifying more classes or less classes or different classes. So I'll just go quickly into this. So like we said, we won't be covering like everything. So just the most important thing that you need to learn. And if there are any questions, feel free to raise them, inshallah. Let me just reshare my screen in 1 minute. Okay. So when this transfer line happens like almost in general, like not just in computer vision, in natural language processing. So maybe if you are common with the LLM terminologies, you might have heard of fine tuning. So fine tuning is also relates to transfer learning, but it's a bit different. So one of the key differences is in transfer learning, what you are training on is like some subparts of the model, which we will see later on. You are just training like the classifier. Then in fine tuning, you are more of like training the entire model itself so that it aligns to some kind of new distribution. But it's essentially like very similar concepts. So in fine tuning, you use like much more slower learning rate because you don't want to don't change the entire model parameters. So quickly, let's just get started. So one of the importance that you can see here highlighted here in transfer line is you use existing model, so it has already been trained before, and then it has already learned the patterns before. So, and one other thing of note is it is much more, let's say, compute efficient because training these models from scratch takes like very long amount of time and effort. So if you already have model that has been trained before on some similar data and you want to train it on your own data set, so use like as little compute as you would have, so you don't need to like spend several hours training them, and you require maybe not so large you just require some, let's say, some adequate data. So because like already it has already learned these features, so you just need to give it some sufficient data and it will be good to learn. But before this, if you're training from scratch, you need like very large amount of data sets. So yes, these are like some additional advantage of like transfer learning. So let me just feel free to ask questions if you have. And yeah, so like where can you find this existing data set? So one of the most popular ones in PyTorch, so it already gives you some existing PyTorch libraries in which you can use. So let's quickly look at them. Just give me 1 minute. Yeah. So if you go to the Touch documentation, you can see lots of existing library, but this relates to like the computer vision one. So there are lots of different libraries. You see AlexNet, EfficientNet. So these are like already pre-trained models, and they already have their own weights. So most of these models have been trained on ImageNet. So ImageNet is a very large database of several images, and it has learned some underlying patterns of those images. So you don't need to train from scratch. So all you need to do is just to get any of these models that fits your taste, and you can build on that. Then we'll look at how we can do that subsequently in the very next few lectures. Then you have Hugging Face. So Hugging Face is particularly popular now, especially with the recent rise of large language models. So any model you are looking for, it's mostly uploaded to Hugging Face. So it's like some global platform in which you find models. Then you have this team. This team is specifically for computer vision. Then you can, let me see. Yeah, so let me just go to, so you can also see, yeah. So you can also see some really nice models here in which you can use, and pre-trained ones in which you can use for all your necessary tasks at the end of the day. So these are just some, so this would be very helpful when you come to doing your course project if you hope to use some pre-trained models. So these locations would be super cool. And you have papers with code. So mostly before now, I don't know how popular papers with code is, but before now, during like 20, maybe 15 to 2020, when it was like the high time of computer vision, so papers with code, most of the papers that are published, they publish their code here, and you find their model also here in papers code. But I don't know if people do use them now, probably for lightweight stuff. But the most popular one now is Hugging Face. So you find different models, if it's audio, video, or text. So you find most of the models there. So yeah, so everything follows like the same workflow we've been working or talking about. You get the data, then you pre-process the data, then train on the data, then you perform evaluations. So we'll just keep to some parts that are important for this and discuss the details. Since we've gone over training before and you've seen how training works, then yeah. So here we are just getting the same data in which we want to classify between pizza, steak, and sushi, as we did for the previous lectures. Then I'll skip that because we've done like a number of things here. Then I'll just highlight some few things here again. So remember when we were loading our data, so we had some transformations, which we want to transform our input, which has been like images from one characteristic to another. So we can perform different, we can do resizing, we can do some cropping, we can do some rotation, just as we did. So, but one key thing we usually wouldn't need to do when doing transfer learning is what we call transformation by normalization. We need to add that in your transfer learning pipeline. So just give me a minute. Yes. So typically, like when these models were trained, they were trained on some data sets, and those data sets has some kind of distribution. So think about distribution as some like space where those images are from. So think about one example, think about distribution. Think about images that have been taken by your cell phone and images that have been taken by a high-end camera. You can see like they are different, they have some variations. So one is like, you can say the distributions from like some cell phone and some of the distributions from like some high digital camera. So if we have trained our model based on some distribution of images that's from like a high digital camera, so expect to do some transformation from that high digital camera to images we've taken from our cell phone, because they are not the same thing. So typically in the same sense with these particular models, the data sets has been trained with is from one distribution, and you want to kind of transfer some knowledge from that distribution to, you want to learn the knowledge from your new data set. So what you want to do is to normalize your data. So typically what we want to do is so images are from 0 to 255 as we discussed in the previous lectures. Then what we want to do is like to normalize them between 0 or 1. So what we want to do is, instead of just doing it on the new data set, we kind of get the mean. So to standardize this to 0 or 1, if you remember statistics, you need your mean and your standard deviation here. So what is the mean and standard deviation? The mean and standard deviation are from the original data set in which the model has been trained upon. So almost most of the models that we've been training on use like the ImageNet data set, and they have this mean and standard deviation of the data sets. So imagine like you stack all the data sets together and you kind of want to get the mean and standard deviation of all the images together along the channels. So you can see here we have three numbers, which corresponds to like the three channels of the images. So you know in an image, in a colored image, typically you have three channels, RGB. So in each of the channels, like you stack the images together, then you take like the mean of along each of the channels. So what's the mean number? So this helps us to standardize any new image coming in because it's from a different distribution as the source image that has been trained upon. So we just want to align it to the same distribution as the original image. Yes. So what we do afterwards is to call this transforms. Remember from our last, so it has this class called normalize, and you pass in like the mean and you pass in the standard deviation here. So into the pipeline. So what happens typically as with most, if an image comes in to the pipeline, so it performs like a set of transformation we've had in mind. So it can be resize, can be crop, then probably what you have here, normalize. So normalize is just to change the values, any incoming tensors from with this mean and your standard deviation. So yes. So here we are just performing, you are just setting out some creating some like compose, as we talked about. This is just a pipeline. So first what we wanted to do is to resize the image. Then the image is likely in some PIL format, some image objects. I'm going to convert to PyTorch tensors. So everything we'll be dealing with is touch tensors. Then finally, we want to normalize based on like the mean and the stand mean here and standard deviation from like the original data sets the model has been trained upon initially. So I'll just run this quickly. And yeah, so most of this, we've covered this. So this is more of like the important things we'll be dealing with. So first, what we want to do is to get an existing model, and we've spoken about where we'll get these models from. So either from Hugging Face or from the Touch Vision library, which has some existing models. So most essentially, when someone talks about the models, there are like two things you should keep in mind. One is, what's the name? The architecture. Sorry, 1 minute. So one is architecture, then two is like the weight. So the architecture just relates to like some kind of graph in which like the input comes in, what kind of operation is performs on the inputs, and you get an output. So easily you can think about the simplest architecture you can think about. Let's say you have some simple neural network which an input comes in, and you have maybe 2 neurons, 3 neurons, and you have like some output neurons here. Let's say this is our network. So this here represents like an architecture that we can have at the end of the day, and we have an output. Then you can have some varying architectures. Instead of this 3-layer neural network, you can have 4-layer neural network, you can have 5-layer neural network. And in any of the layers, perhaps maybe here, you can have maybe 10 to 20 neurons. So this is like an architecture. So one other important thing is like the weights. So you know, in this network, what you are learning is to learn some kind of underlying representation or transformation, and you learn some numbers. So for instance, here it could be 0.5, here it could be 0.8, and so on and so forth. So these numbers here represent the weights. So these are like the key things when anyone talks about model. One is the architecture and one is the weight. So, and they can't do without the other. So first you need an architecture. So with an architecture, you know what is the structure of the model, and you can initialize it randomly. So when you initialize the random, it means your model has not maybe any idea of what it has learned. Then you can either load the weights. So in transfer learning, what we do is we get the architecture and we get the existing weights because someone has helped us train it. And from there, we can use the weights and use it appropriately to our own test. So what we are doing here is from this, so we can load the weights in the sense we can call like vision model, and this is the name of the model weights. And here we call like default. So default here means this is like the best existing model. It has like the best performance based on this model architecture here, like EfficientNet B0. So you can have like, you can load any model you want and load the weights as required as you want. So but here in this example, we'll be using EfficientNet. So in your project, you can use any of the networks that you want to use at the end of the day, inshallah. So first, what we did here is load the weights. And so the weights, you can see it's ImageNet, and it's like version 1 here. So this is like the best widths available for this particular model. So because it's, we call default. So but if you want, you can call any, if you have any reason to create any other version, you can call it here. So typically it can follow this kind of format. Maybe you can have V2. And how you can see that is, let me see here. Yeah, let me just clear this. So you can consult like this page and see what's available. Then here you can find like the weight you want to use. So here you can find this 1K V1. And I think for this is like the only weight available, but probably for other models, they might have existing weights available. Yeah, so, but this is for this. So if you want, you can check out like the source code, and probably you will see, let me see. Yes, so I think this is likely like the major existing weights available for this model. Yeah. So yeah, so that's major, but you can consult this page to see what other weights are available. But by default, if you kind of put in the default keyword, or if you call the default attribute here, then you get the best existing weight here. So here, we'll just run this. And with the weights here, what it comes with is transforms. So this transforms here is just similar to like the transforms we've been talking about. How can we transform the image before passing it into the model? So it tells you what transform it happens with the image. So first, what can you see? You can see first you crop the image. So let's say the image is of some particular size, no matter the size, then you kind of crop part of the image. Then you resize the image to 256 by 256. So even though it's just one number, it still like relates to the same thing. This is 256 by 256. So yes. And what next do we do? Then what next we do is like the normalization, like we talked about. So it's from the model has been trained from like some data set that has some existing distribution. So what we want to do is to standardize our own incoming images or test images to this particular to similar distribution as the original data sets. By using this, then finally we do some kind of interpolation just so that we get like the new resulting like image. So remember, when you want to resize, so there are different methods you can use bilinear, but don't focus about that. So when you resize an image, so there are different like methods you can use. You can use some bilinear interpolation or this bicubic interpolation, just so that you get like a better resolution if you are scaling the image. Either you are scaling down or upward because you are losing some information or trying to gain some information. So you can think about like moving from like low resolution to high resolution images. So moving from low resolution to high resolution is a bit difficult because you want to maintain the information available in that image. So you need some kind of method so that will help you scale up. Yeah, so that's where this interpolation comes in. So what next? So here data loading. So I'll just skip this. And so as we said, you have like different variety of models available. Then these are like some common ones like some years back, which is ResNet, VGG, EfficientNet, Transformer, and the rest. So, but for this particular session, we'll just only be using EfficientNet. So one important thing for you to note, each of these network have their own advantages or their preferences and where they are good at. So, and the important thing, they have research papers on this. So if you want to look at like ResNet, for instance, let me see. Just give me 1 minute. Okay. So let's say you want to look at, let's say ResNet. So it has some own research paper. So one of the projects we're talking about, it's like how you can also read research papers and try to implement them for any of the project applications you want to make. But each of this like have some key idea within them. So in the previous lectures, we talked about like CNN, convolutional neural network, and how it helps to identify images correctly. So all of these models have like some form of CNN in them, but they have some kind of key ideas in each of them. So I'll just briefly explain that. But if you want to go deeper, you can check out the paper. But here, I just want you to get familiar with the models a bit and learn to use them with PyTorch. Subsequently, we get to show you how to build these models like from scratch and build them. So let's see, you are looking at, we can look at this, let's say ResNet, for instance. So the key idea of ResNet is, let's say you have these blocks of maybe CNN, and maybe several block of some convolutional neural network, which also contains some sub-component, and you have some input image coming in here, here, here. And maybe finally you have some MLP layer, and you have your output finally. So what happens in ResNet is, yeah, so instead of having this linear pattern or movement, so what they propose is, why not we have some skip connections? So maybe you can skip here, and the input here goes to the next layer, and we add them. And their own intuition is with this kind of architecture, so it reduces like vanishing gradients or exploding gradients. So because this network is very deep, so as you go with time, and when you want to do like back propagation, so most times your back propagation might be 0. You might have values of 0, and you don't want that. Or it might be very large value for your gradients. So the idea is our gradients vanish. So why not we have this skip connection, and the output from one layer jumps to the next layer, and we add them up. So it helps like stabilize learning at the end of the day. So that's their key intuition. Then you have models like also like VGG. So each of these models have their own like key advantages. Just give me 1 minute. So you have also models like VGG. So the key idea of VGG is like, so instead, typically what you have in these CNN blocks are like cascades of several convolutional networks and some other operations and some pooling. So why not we use a uniform network? So let's use a 3x3 filter in all of our CNN networks. So when you use a 3x3 filter, they kind of see it performs better with time. So each of these works like have their own approach to how they view things. Then you have like the efficient net in which we'll be like working with. So the key idea of efficient net is, let me see, just give me 1 minute. So an efficient net is, so how people try to perform like to improve on these models is either by width, to improve, like increase the width. This is like the channels of the CNN, or what, you increase the depth of the network. This is like the number of layers of the network, or resolution. So that's the input of the image. You remember we talked about how images can have like several size. 256 by 256, the higher the number, the higher the resolution. The lower the number, the lower the resolution. So what they try to do, so each of the previous model, what they do is like they take one of this, either work on the width or work on the depth or work on the resolution of the image. So with EfficientNet, they say, why not we combine everything together? And they found out actually it was better. So you have varying width of the channels and varying depth or varying resolution, and they found out it was better and uses lesser parameters as needed. So that was like one of their key ideas for the papers. So let's quickly look into like this model. So each of the model, you just look at like what happens or how important it is and how it fits your work. So if you are trying to build like a low level computer vision model, so, and maybe you would want to use in like some low-level hardware, let's say Arduino or microcontroller. So you don't want a very massive model because it consumes a lot of memory. So you want to go for models that are like smaller in size. So EfficientNet might be good because it's smaller in size and also has relatively better performance than the rest of the models. So if you are maybe perhaps training the model from scratch and you're not thinking about deployment, you might want to go for larger models like ResNet. It has like varying sizes depending on the depth, and you want to train it on that. So depending on what you want to achieve for the task at hand, then you think about it. So this is also a talking point when you come to do your project. Like you chose this model because of XYZ, and you can talk about it in your project. So yeah, quickly we'll just look into, yes. So here, what we have is, so as we talked about, first we have the weight, and we can call the weight with this touch vision models and EfficientNet weights. So this can be any model weight, but you must make sure like the weights. Okay, I'll come to that. Then here after that, we call default. So this default means should get us the best available model. So it can be any value. So depending on if you have preference for other kind of model weights available. So most times you have like different versions of the weight, but typically the best model, you find them in like default. So the best models means the model with the best performance, which is mostly accuracy because it's a computer vision task. Then finally, what you would need to do, remember we said you have the weights and you have like the architecture. So here we've loaded the weights, then here we have the architecture of the model and we are passing it the weight here. So if we don't pass the weight here, so what happens is it initializes the model randomly. So it's like a model that is that has not learned anything. But here, because we are passing it the weight that we have here, so it has a model that has learned to do some particular task, which is the ImageNet task here. Then here, what we will do is, yeah. So we kind of load the weight here and move it to the available device that we have here, which is like the GPU in our own case here. So here we've loaded the model and we can see what the model architecture is. Just give me 1 minute. So as we talked about, like there are two components, the architecture and the weights. So you must make sure like the weight you are loading the exact weight to like the same architecture, because when you load the model weights to some architecture, so it gives some error. So maybe we can try something here. So let's say we load this B0 weight and maybe we load it to B1 architecture. Then you can see it raises an error, invalid weight class. So it has to be like the same weight to the same architecture. And it kind of makes sense because let's say you are having some 3-layer neural network, you can't load a 5-layer neural network weight to it. So here we can run this here so that you can see what is existing. So typically these models are arranged in blocks. So first you might have maybe features here, but this is like just naming. So it doesn't mean anything. So when building your model, you can name it anything. So you can name it blocks or anything. So these features here represents like the CNN layers. So multiple stacks of CNN. So you can see it has sequential, we discussed sequential, and you have like one block of some CNN layer, and you have several other like subsequent blocks of CNN. So after these features, so features here majorly comprise of CNN blocks. Then finally, after your CNN layer, in which you've seen in the previous, you want a classifier. So let me see. So towards the very end, yes. So towards the very end, you have like a multi-layer perceptron, which does the classification for you. So this, it collects an input feature and an output feature. So remember we said like the output here is, let's say the number of classes we want to predict here. And the input here is after it has performed all those convolution operations and you flatten it. So this is the resulting like feature dimension here. So just like some kind of very flat dimension of 1 to 80 values. But out of this 1 to 80 values, you want to predict the number of classes. So you have to set the number of classes here. So here we'll kind of see how you can change that when doing transfer learning. Yes. Please feel free to ask any questions you have on the chat. Happy to answer them. Yeah, so that's like our model. Then, yeah. So let me see. So I'll just skip a bit of this. So if you just want to get more information about the model, so you have this touch info library. So this touch info library gives you has a kind of module called summary. So it gives you a summary and you can see what's happening within the model. So we can briefly look into that now. So what you need to do is, this is like the library module, then you pass in your model. So this can be any model. So it can be a computer vision model or a very large neural network model. Then you tell it your input, your assumed input size. You're expecting a batch size of 32, channel 3, then this image dimension here, 24 by 24. Then these are just some extra parameters, so you don't need to worry about that. So this is like the columns you want to see as output, then the width, then the variable name. But don't worry, the much more interesting information is here. So it tells you like sequentially what happens as an input comes in. So here, this is the input we have coming into the model, and it goes into, yeah, so this is the entire model itself. Then you have like something like a tree. So at this first sequential layer, so what we expect is we have an input of 32 by 32 of batch size 32. Then you have like channel of 3. Just you have your input image. Then at the end of these features layer, what you have is 32. Then you have some dimension of channel of 1 to 80 as we've seen. Then you have 7 by 7. So that's what happens in the sequential layer. So the sequential layer is more of like, or the features layer is a stack of several convolutions. So when you pass in your image, so it tells you like, this is the output you should be expecting as your image. Then when you perform other subsequent operations, then you see what happens at the end of the day. So let me just go to the last part. Yeah. So here we can see after the features layer, it comes into this average pooling. So average pooling automatically just does average for you. So from this output that we have of our CNN blocks, then after performing average, then you have this 32 by 1080 and 1 by 1. Because of the average, the 7 by 7 has been kind of reduced to 1 by 1. Then you flatten, that's where you have your 1 to 80. Then from there, you can apply a linear layer. And you can see from that 180, we can get our classes here. But what happens if you have a different number of classes? How can you change that? Then we will look into that. So just be mindful of what is the name of the classifier or your MLP block. This is like the classifier. We call it here classifier. So that if you want to change it to some number of classes, you can easily change it. So I will just speed run a bit. So most of the information are there. And also, I think one key thing that I forgot to mention is by the right-hand side here, you can see if each of these blocks here are trainable. That means you can train them. So that means you allow gradients to pass through them, and you have some number of parameters here in this particular column. So quickly, I will just go. So at the end of the day, what you want to do for transfer learning is you have, well, okay, let me do, you have, let's say an image, you have, or images rather, then you want to pass it into some model, and you want to get some maybe output here. So this model is consists of several like CNN blocks. CNN, like a lot of them, and CNN. Then you have some maybe MLP layer. So this MLP layer is your like classifier. So typically, like we said, with the CNN blocks here, just give me 1 minute. These CNN blocks here, you can think about like some feature extractor. So it has learned to extract features of any kind of images that come. So no matter the kind of images. So think about what we talk about. Let's say we are identifying cats and dogs. I learned to identify the shape of the face of the cat or some distinct features such as the eyebrows or any things like colors and the rest of the day. So you don't want to change that because what you want to learn is just how it can predict new classes. So it is already a feature extractor. So what we would do here is just to freeze these blocks of CNN. So we don't want to retrain it again because it has already been trained, and our assumption is it has learned from the massive data available how to extract these features effectively. So at the end of the day, what we want to train is this MLP layer here. So that's like our main goal in transfer learning, especially in like computer vision. So this CNN, it's already there, a feature extractor, you don't need it. So it's already been trained. So think about it like some kind of filtering system that's already been developed for you. So you don't want to train that again. So what you want to train is how it can identify the images better. So that's where the MLP layer is the only part we will get to train at the end of the day. So it's much more efficient. So as you can see, we don't train like the entire neural network. So that's what makes transfer learning cost efficient. So we just train like a very sub layer of the neural network. So which makes it better for us. So how can we freeze those layers as we talked about? So remember our model, it has like these features. So these features holds all the CNN blocks that we had in mind. Then we can call parameters. So when we call these parameters method here, so what it does, it calls like the original nn.parameter. So this is where like the weights are stored. So when you call that, then what we do for each of the features, we kind of set this requires grad to false. That means we don't want gradients to flow within that part of the model. So since we don't want gradients to flow within that part of the model, that means we freeze it. So nothing is happening, nothing is getting updated within that part of the model. So yes, and we can run this. Then finally, so the last part we want to change is this part of the model which says classifier. So why we want to change that is originally it learns to predict 1,000 outputs. So it learns to predict like 1,000 classes, but for our own example now, we just have 3 classes. Then we need to change that. So what we can do here is to specify a new classifier with this particular network. So we add a dropout and we add a new linear layer. So the new linear layer, what it has is, it has this new output shape. So this output shape just reflects our number of classes, which is 3, because we are predicting 3 things, which is pizza, steak, and yeah, it's like 3. So I've forgotten the third one. So yeah, so that's why we have that. So, and just to explain dropout. So dropout simply means it's a way to regularize your model. So since you're coming from machine learning background, you know your models can overfit. So they become like too intelligent, and at the end of the day, they memorize the data that you've given it. So, but in this case, we don't want it to memorize, then we add dropout. So dropout simply means, let me give a very quick illustration. So let's say we have this, let's say we have this set of neurons here. Let's say 5 neurons. And now let me just mute. Yeah. So let's say you have this neurons here, like 5 neurons, and you have like input coming in. So typically without this dropout, each part of the neuron here takes part in the computation of any input coming in. So because you don't want it to overlearn, so you want to add dropout so that maybe for any instance of the input, maybe this neuron here will not take part in the computation. So just the remaining 5 or 4 neurons. So that's the idea of dropout. So each of the neurons might likely be skipped computation, and you might not perform computation on that. So that helps you a lot when you are dealing with overfitting. So because not all the neurons are learning, so just sub part of the neuron. So it kind of helps you to diversify your learning, and you learn better at the end of the day. So typically with dropout, what you set is this p-value. This p-value just means like probability of how each of the model will be skipped. So here we set a probability of 0.2. That's 2 out of 10 or 1 out of 5. So what we typically mean here in one, let's say you are, so out of 1 out of 5 chance that each of the neuron would be like skipped for training, or you will not use each of the neuron. So there's like 20% chance. So let's say an input comes in, there's a probability of 20% that that input or that neuron will not be used for training. So it's more of like just ignoring it for that particular input. So but for subsequent inputs, then you can probably use that neuron. So I think the major idea for dropout, you don't use certain neurons based on some certain probability, and it helps you to prevent overfitting with time. So yes. So after this, so what we typically have, we have a model, and in that model, we are only training like the classifier part of the model, not the CNN blocks, because the CNN is like a feature extractor, which has been learned over time from some very massive data sets. So right now, what we will want to do is like to train the model. So this training pipeline follows how we have been training models, like the existing models all along. Nothing changes. Everything is the same. So for that, I will just skip the part, because the major part I wanted you to grab is what happens within the transfer line itself, and you train the model itself. So here, this is like an existing training pipeline. So what you can see is it starts with a high loss and kind of decreases, because we want our loss to go as low as possible. So it shows us like our model is improving with time. So you can see for like just 5 epochs, it has decreased from 1 to 0.6 for the train loss, and also for the test loss also. So, and you can see the plots here. So just give me a minute. Let me just see. Yes. So for the plot here of the loss, for the blue, you have it decreasing, and for the test, you have it decreasing. So for this plot, quickly, can you tell me, like, is our model underfitting, overfitting, or is it just correct, or is it usual? So you can just quickly type in the next maybe 1 minute. So what do you think about this loss curve or accuracy curve? Do you feel it's overfitting, or do you feel like there's some kind of issue, or is, if you want, you can quickly unmute and maybe talk briefly. So what do you think about the loss curve? We described some loss curve previously, and how you can have some overfitting, underfitting, and loss curves that are just like very much okay. Yes, so there's a comment by Yahya who says that it's just usual, which is good because it's decreasing. But one interesting thing that you might notice, and there's comment by Sophia, which says like overfitting, which arguably is also correct too, because typically when you are training this model, you want the loss of the, typically because you are training based on the training data, you want the training loss to be lower than the test loss. And but this is not the case. So why is this not the case? So it's likely that your training data has much more complex examples. So because your training data has much more complex examples, it has learned like very complex things, and but your test data has much more simpler examples. So that's why it's easier to like have a higher accuracy on your test loss. So that's like a likely scenario. So it's okay now. So everything looks fine and good. So just a scenario in which maybe your test data might be too simple and nothing too difficult to predict on. So, and your training data is much more complex. So that's might be one of the reasons you might have here. So yeah, thanks so much for the contributions. So I would say then finally you will get to predict on some images and test it out, and you get some probability. So, and you know, you just take the maximum the class with the maximum probability. As you can see, our model here has learned to predict sushi and also pizza. Then you can try out on some real world images here as you have. So in just talk briefly about like the course project. So one of the ideas is to like solve some existing problems or real world problems using any of the models. If you want to train from scratch, it's fine. And if you want to use any of the pre-trained models, it's fine. Then you can build a pipeline for testing out these images. So it's also our expectations for you within the project as you work in group, inshallah. So that's majorly it. So I think there is like 1 or 2 questions, but if there's any questions, feel free to ask. So there's a question from Abdul Ahmad. If we match 2 architectures together to create a new model, is the process the same or there are adjustments? So if you match 2 architectures together, so it depends on how you want to match. So because there are several considerations in merging 2 architectures together, but I would say it's the interesting thing you can do is to match like the ideas of several models, as we have talked about in EfficientNet, how they match like the contributions of several models together. And so you can do that. But if you match 2 architectures together, so it gets complicated to load the weight. So you either match 2 architectures together, then maybe train from scratch. So it's possible to have like better results. So it's also likely to have some not so good results. So it just depends on how you do that. Yes. So because with thing with deep learning is sometimes you just trial and error. So you might try something and it works really good. And there's a question from Sophia. Can you explain how to train the model to predict really well on your own data sets? Yes, so because the training that we did now, it's on our own data sets. So this, because initially the model was trained on ImageNet dataset, a very large data bank of data sets. And now we have trained the model to use our own data set. Let me just see 1 minute. So this is where we loaded our data sets here, from here, in this particular instance. So let me see, just give me 1 minute, I'm coming. Yeah, so in this particular instance, this is like we are using our own data sets. And yeah, so this is where we loaded it. Yes, Sophia, you can unmute your mic if you want to speak. Yes.
Hi, good morning.
Hello, good morning.
My question is that the
Mm.
part you said that we have to, like, maybe the model is trained on different data sets. Maybe we know the model is trained on classification,
Mm.
and I want to use it for my own different classification that is different from their own classification. So
Yes.
you mentioned dropping down their own features.
Yes.
So that part I don't really get
Ah,
it
oh,
very
okay, I
well.
see, I see, I see. Okay, let me quickly explain it again. Just give me 1 minute. So, yes. Okay, let me just go to this. Yes. So, yes. So let's say, assume this is the model architecture. So entirely for this first part of the model, so it has like several CNN blocks, that's convolution blocks. So with these convolution blocks, it just learns, what's the name? It just learns like feature extraction. Then what does the actual classification is like your linear layer here. So, but for their linear layer, so they have an output of 1,000. So they have like 1,000 classes. So it's likely the case when you are doing your own tax, you have less than 1,000 or more than 1,000, or anything can change. Or you might feel you need much more linear layers. Then what you need to change for your own data set is like this part of the architecture here, the classifier here. So this is like the only part that you'll be training. All other parameters above are, or all other like, parameters above are being frozen. You don't need to train them because they are just helping to extract features. You don't want to learn anything from that. So you just want to, instead of predicting, let's say 1K classes here, you just want it to predict like number of new classes you want. So this is the most important part for, let's say, transfer learning. And maybe if you want to also train, if you have a very massive amount of data, you can try training like the layers above. So what we do here is, you can see this has like a dropout here. Don't bother too much about it. It's just to you can do without dropout. So dropout just means to reduce overfitting. So if you're familiar with overfitting, you don't want your model to memorize the data set. So what the most important thing is like the new layer architecture here, which is like the linear layer. So instead of having an output of 1,000, so instead you want, here we have 3 classes. So we change it to have an output of 3 here. So of output shape 3 based on the length of our classes here that we have. I don't know if that answers your question.
Yes, it does. Thank you
Mm.
very much.
Yes, yes. But if you want any clarification, feel free to like text on the message on the group. So Discord group, happy to talk more about it. Yes. Yes, so I would say, yeah, thanks so much for joining. So that's majorly it. And please, as always, just if there's anything, just message us on the Discord channels. So we are still on the like submission assignment, so we will
Sorry,
update you.
please. About
Yes.
the assignments, I've submitted like 3 or 4
Ah,
assignments now, and
eh.
I've not gotten any feedback yet.
Mm-mm. Okay, so sorry, we will get back to you because like the number of people are a lot, so but we'll get back to you as soon as possible. So you would probably get all the reviews as soon as possible also. So but just also keep up making the submissions and we'll get back to you with the feedback. Yes, and I think there is also some comments about like the assignments. So maybe for some individuals, more of like copy and paste because there's an existing solution. So because our goal here is to make you understand, so not just to maybe submit. That's like, I'm talking in general. So for anyone maybe watching the video subsequently, so it's always good to try things out yourself and make the mistakes and learn from it. So that's how you can build your skills, not just submitting at the end of the day. So, but I think it's good. You just follow up with the assignment because with the assignment it will help us put you guys in groups. So those that have submitted the assignments, so we can put you in groups so that you can be able to work effectively. So yes, this is like the sixth session or maybe sixth or seventh, but six based on like the main sessions we've been having. And I believe we just have 2 more sections before after Ramadan, you guys will have a chance. You'll be paired in groups to do to start your project proper, and we'll be guiding you along the way. We won't just leave you alone, inshallah. Yes.
Assalamu alaikum, sir.
Wa alaikum salam, Shams. Yeah.
Sir, please, can I have your contact, sir? I want to consult you on some project. I'm conducting personal project on transfer line, so I may need consultation from you so that I can have your guidance.
Yes, yes, yes. Just feel free to, I think, yes. Are you on the Discord?
Yes, I'm in Discord group.
Yes, please message me on Discord. You can send me a
Okay, sir.
DM on Discord. So happy to answer you. Yes. Then we can see how we
Okay.
can talk, inshallah. Yeah.
Okay,
So
thank
I
you.
think that's majorly it for today. So in the next subsequent lecture, will look like differently beyond what's the name, transfer learning, and how you could like track your metrics. So in a very complicated scenario in which you need to like track this training loss and you're training like several models and how to replicate different papers, because here we have highlighted a few papers like efficient nets, so how you can replicate building those models, inshallah. So I believe we just have 2 more sessions with you before the end of Ramadan, then we'll let you be and with the projects, and we will have weekly guidance of the project, inshallah. So that's majorly. Thanks so much for joining the class. I hope you have a lovely rest of the day, inshallah. Bye.